So I did press the record button. I'm going to put my mask because I cannot afford to become ill. I press the record button. This does not mean that you can stay home, unfortunately, and log in on Zoom. This class is mandatory attendance. You have 2 unexcused absences throughout the semester. Most of the times people are using it for illnesses. Do not come to class if you're ill. Okay. Just do what I will tell you in the ticketing system a little bit in the next 5 minutes, and then you will be okay. Now, if you go beyond the 2 illnesses and something serious happens to you, not good, but I think there is a system where you can have NYU email me, and then I'll provide accommodation depending on what I'm going to hear from them. Okay, most likely you need a doctor's note of some sort. So two unexcused absences in the population of 14 lectures or 13 lectures, I think, is plenty. I think, and so everyone is mandatory attendance. I'm not going to take attendance right now because I just did, but next week there will be a piece of paper that you will be signing in, and just to mark attendance until we find a better system in this century. If you go beyond 2 without any excuse, then there will be a double-digit decrease in your total grade. I want to be very strict about it. Okay, it's in mandatory presence here, and there is always you can make both arguments as to I'm more productive at home, blah blah, and so on. But yeah, I think for this class at least you need to be here. This meeting is recorded. How can I get rid of this? Okay. All right. So let me introduce myself a little bit. I'm instructing this class since 2020, for a long time now, and I think overall, my permanent position is at an institution called NJIT. It's another university in the area, and I'm also I have my own consulting firm on the space of AI, gravitating towards perception and robotics. That's it's my kind of love affair per se, but these days everything to one way or another involves some form of a language model. As I said, we out of our experience, we know what is working, what is not working, even if in this kind of a hybrid class scenario. One question that I have specifically in spring is that, okay, I'm an undergraduate student. What's going to happen in the exams and finals and things like that? Well, good news is that good news for the master students. The exams and the finals, the midterm and final, are going to be one and the same. Okay, that is good news for master students who are typically coming with a much better background in this kind of class. We don't going to have separate exams between undergrads and graduates students. Also, good news with respect to assignments. The assignments will be what it will be. Okay, and for both populations. The class has been receiving very good feedback from a variety of backgrounds, even those who come into this kind of class without really having gone through another machine learning kind of course and strong programming sort of background in Python with frameworks and things like that, like Torch, TensorFlow, and so on. But the first few weeks of the course are extremely critical, especially those who don't have this background. Okay, criticality is from the fact that we are providing some pointers. First pointer arrived in your inbox is when? When did I send out the first homework? Not homework, but preparation, sort of invitation to prepare yourselves. January 12th, right? So who has received it on January 12th? Who has seen it January 12th? Okay, so some of you saw it, some of you didn't really see it. That's fine. But now that you all know how to get into Discord, Did you receive who is in Discord? Who is not in Discord right now? Don't hesitate to raise your hand if you are not. One person, two persons, three persons, four, five. Okay. So are you in the right class in the sense that are you in Brightspace? Did you go to Brightspace? Yes. Did you see the announcement? Did you receive the invitation to join the server? You're on it right now. Okay. So make sure that you follow the steps. Go to announcements, join the Discord server, and you will see these messages. There will be lots of messages. Let me show you. Where is Discord here? Come on. All right. So where is your class? Class is in person. Okay. So that's the first message. That's the first message. It gives you a website, some tasks to do to prepare yourselves on probability theory, right? And some other kind of background material. This course specifically stands for CS109. It's a good course to learn a bit about random variables, things like that. There are some other kind of prerequisites here about calculus, right? Khan Academy, multivariate calculus is plenty. And obviously in the linear algebra space, we are going to require you to understand basic things like dimensionality reduction of vector spaces. Okay. Which is pretty straightforward stuff. I mean, it's not really nothing to be afraid of. Now, we are in the process actually of migrating this site to some other destination. We will let you know when this happens. The content will remain the same, but it's just the URL will change. Okay. Now, in the same Discord, the two TAs, both of them all of my TAs are former students of mine. These guys have been with TAs for at least 2 or 3 rounds. So they know very well what's going on in the class. Have already introduced themselves. And very soon, they will also, in the same kind of thread, introduce another critical piece of information, which is their GitHub ID. Okay, you need this piece of information because you're going to add them as collaborators in your GitHub repository, which is the repository via which you will be submitting your assignments and potentially the project, it depends, in this class. Okay, who is in GitHub? Who is not in GitHub? It's okay not to be in GitHub, it's fine. Okay, hopefully everyone is. Who is in Hugging Face? Who is in Hugging Face? Now, only a very few people are in Hugging Face. Go ahead and create a Hugging Face account. Okay, you will need it. Hugging Face, you just Google it if you do not know what Hugging Face is. It's a destination that has nothing to do with hugs or anything else, okay? It's a technical destination, let's say. You should know that sometimes I'm using black humor or some kind of English version of humor to break the ice and make a point. Okay, hopefully everyone is fine with it. Okay, so what happened? So the next message I want to see, okay, the two TAs introduce themselves and they will post their GitHub IDs. We will see a bit later when you're going to use them, use the GitHub IDs, that is. The other destination in this site, there are two things that you need to do when you join the Discord server, which hopefully everyone has done. The first is that you need to be fully identifiable in the Discord server. First name, space, or dot, last name has to be your nickname. One of the assignment 1 tasks for worth of 5 points is to change your nickname. If the TA see that you have not, they'll take 5 points away from your grade. Okay. For every assignment that this does not happen. The other thing that you need to be familiar with is you can, after you change your nickname, you will be able to use the famous ticketing system. What is a ticketing system? Just like any other ticketing system you may have used, you press the button, create ticket, And when do you press the button? What are the typical use cases? You are certain we have done a mistake in your assignment grade, your grading process. It can happen. It's not very frequent, but it can happen. You open a ticket, says reservation. I have my reservations with respect to assignment 1 grade. Okay, and then you put some descriptions as to why, and you press the submit button. The ticket is private between me, you, and the TAs. No one else is able to see the ticket. After 48 hours or within the 24 hours, typically within 48 hours, we are responding to the ticket. The only exception is when it's a weekend. Okay? And we also have our lives, right? So it's obviously reasonable to expect longer latencies then. And then we try to resolve it. After we resolve it, you have to close the ticket. Okay, there's a button to close the ticket and the ticket disappears. Make sure you close your tickets because it helps us respond better. Be a good citizen of the ticketing system. Okay, because if we face, if we see 60 tickets and we do not know if it is closed or open or still requires some attention, then we spend time browsing. Okay, any questions on the ticketing system? The tickets cannot be used only for regrading or some kind of issue with the grades, but it can be used in other ways as well. The most important and most useful and usual way that people are using the ticketing system is when they want to get some help, either with an assignment or with a project, and somehow they feel reserved to broadcast that question to the class chat. There are pros and cons. If you are too much concerned, please go ahead and open a ticket for that. If you are not, please go ahead and for every assignment, there will be a thread where you can actually post a comment or a question and things like that. The benefit of doing it in the class chat is that everyone gets to benefit from our answers. Okay, that's basically the other most useful way. The third way is to open a ticket, is to get hold of me. Okay, the single most important constraint in this kind of class is unfortunately my availability, because I have 2 residencies in the US. I have a Boston residence, I have a New Jersey residence. I am commuting between the 2 cities. And another constraint is when I park my car, closes at 7:45. So I have to finish here at 7:20 and run to the car. I don't want to spend my evening in New York without the car. Okay, and go back to New Jersey, which is yet another fun action, end of the week activity for me. Okay, so I won't be able to stay to discuss with you. Having said that, I am here in my office in J Street. You know where the office building is, on the 8th floor. There are a couple of offices which are for adjuncts, and I am here typically at around 2:30. 3 p.m., however, especially in spring, I am starting to discuss with the online version of this class, which is in sync. So there is a time between let's say 2:30 and 3. If you message me ahead of time, I can try to be here at 2 and discuss with you in person. Okay, but most of the time, what you do, you open a ticket. You say, hey, I need some help. I cannot understand this thing. And the TAs were not really that helpful. The TAs will have regular office hours. But let's assume that you're not satisfied with the responses. You click, you open a ticket, and then we agree on a time. Do not send me a Zoom invite. Send me a Google Meet invite with a calendar. I need to have it in my calendar. If I don't have it in the calendar, I won't be able to talk to you because I will forget. Okay, I need to have it in my Google Calendar. There is a link on the course side on how there's some kind of issue with Google Calendar. It seems some people do not know how to use the calendar invitation. So there is a link on how to use the calendar invitations in the site, if you haven't done it before. Okay. Any questions overall on the Discord? Are we okay? Any questions? No. All right. Okay, so expect your assignment 1 to show up sometime this weekend. Okay. And one of the first activities in assignment 1 is to set up a development environment. You may not strictly need it for assignment 1 because this assignment 1 is typically the easiest assignment, and you can still do the assignment in Google Colab. But as the course progresses, you will find it more and more difficult to work with just the Google Colab. I'll come to the development environment and Google Colab when we discuss a little bit the site and the corresponding, go through the corresponding pages there. All right, so let's move on now to the site. I'm going to be using the old site. Is it over here for this discussion? And I'm going to go through the grading distribution. By the way, this is the link where how can you send an invitation to someone with Google Calendar so they have it in the calendar and they can alert 15 minutes before they invest. Midterm 20%, final 30%, project 20%, and assignments 30%. What you don't see here is credit for participation. You don't see credit for participation because there is a penalty for non-participation. Okay, so we don't want to put it as a credit, but there is going to be a penalty, as I just told you a few moments ago, if you exceed the 2 unexcused kind of absences. Obviously, these are these here are still valid for you. And that's basically it. Any questions on the grading side? Right, so let's now move on to the syllabus. All right, so I'll just so there are 3 books quoted here. The first one is a classic, it's not free. Now, this book is a classic for a reason. Obviously, it's a very well-written book. And there are 2 advantages of getting it. One is that we will be using it in a limited number of chapters or topics that we'll be discussing. The other advantage is that it's a very thick book and it looks good in your bookshelf, right? Especially when you're interviewing and you have your bookshelf on your background. So that's the reason why you want to get the first book. The second book, which is a book that is a best-selling book in the space of machine learning, especially when you get starting and to understand how statistical machines can be built, either with neural networks or with linear models, is this one. Now, in its third edition, this book is free of charge to all of you. Okay. Now, I will describe now how you can get access to this book, but not only this one, but also to thousands others which are of similar nature, programming-oriented. This library contains very hot books like, what you see on YouTube these days, like AI engineering, LLMs from scratch, thousands and thousands of books, video courses, cloud engineering, certification material, etc., etc., etc. So if you're in front of the computer, that's fine. If you are not, you can do it at home. So you press this plus button, you type O'Reilly, and you go into this destination, learning.o'reilly.com. Can someone of you who has not gone through this process do it right now and tell me if they are successful or not? You can download the iOS or Android application as well in your iPads and phones. But either of the two, web or app, is exactly the same process. So who's going to be our volunteer for this? We have no volunteers for becoming a volunteer. Okay, one person are here, that's enough. So did you go here?
Yeah.
All right.
Sign in.
Did you sign in? You sign in with your NYU email address. Go ahead and do it. and then you will be redirected to the single sign-on. Let me know if anyone of you, any other person is successful. Did you see the single sign-on? Okay, did you log in with your single sign-on? Good. So do you see something like this here? Good. One person is plenty. So if one did it, so I'm sure the remaining other people who have not done it yet will do it as well. And therefore, we are able to access now a whole bunch of other books associated with programming, anyway, from simple stuff to whatever you can think. So if you Google, if you search here, hands-on, one of the books that will come up is this book that we are told you to start reading. Hands-on. Do you see that third edition? Okay, this third edition is your book. So click on it and add it in the corresponding playlist. All right, so that's how you get access to the second book and other books, okay? Now, the bad news about this book is that it's written for a specific framework called TensorFlow/Keras. And many people are these days in PyTorch, right? Having said that, there is no such thing as equivalent book in the PyTorch kind of space. What I have done over here is I have provided yet another book called Dive to Deep Learning, who is a multi-framework book. So for every concept they have in separate tabs, the Keras code, the PyTorch code, and JAX and other frameworks that are there. Go ahead.
Yeah, they released one for PyTorch last month.
Oh, last month?
Last month.
That's good news. But you see, you learn something every day. Is it fourth edition?
It's also Rally Media. I'm not sure what it is.
Is it the fourth edition? Because this is the third edition, and the title has Keras and TensorFlow, so they released most likely a different title.
It's a completely different book.
From the same author, Jerome?
No, not the same authors.
Okay. All right. That is not the same authors yet. So I have not reviewed that book, but if you send it to me, I will review it. I'll review it. So free of charge, deep learning by the famous book by Ian Goodfellow and company, probably the most theoretical book of the three, specifically in the domain of the deep learning. We will use extensively this book in various sections. Despite the fact that we are giving you books, we are not going necessarily in any kind of chapter 1, chapter 2, chapter 3 kind of order. What happened? We are not, as I said, we're going through chapter 1, chapter 2, chapter 3 kind of order, but we are using the course site, our own kind of course site, to drive the progression, because we are bringing everything from the ground up. Okay. So the good news is that if you do not have the background kind of earlier, this is a great opportunity to bring this kind of background up to ultimately be able to interview into companies that are worth working for. Because as you know, there are companies not worth working. Okay, so that is basically our approach. So in this respect, there are no slides, and no one is clicking through material here, but we are in the mode, all of us, of writing. Writing in iPads, writing in a piece of paper. I'll explain the difference between the two. If you write what I am writing over here, you will get to bring your handwritten notes during the exams. Okay, both midterm and the final exam. Now, let's assume that despite the fact that you are writing and you're trying to follow, the videos are going to be recorded, you listen to the video one more time, you don't understand anything. Okay, I'm not really the best instructor in the space anyway, so let's assume you found a YouTube video at home, or ChatGPT is explaining it 10 times better than I can. You take that explanation that you understood from, and you handwrite it to in the same area as your other notes in the lecture. This means that your notebooks, if it is hardbound notebooks, they will not satisfy that requirement. You need to have notebooks that you can insert stuff in between, right? In order for you to augment the notes that you're going to keep in here with more stuff. And you take the whole thing in this analog format and you bring it here in the exams. The exams are going to be completely analog. There will be no computers, no smartphones, no iPads, nothing. If you keep notes on an iPad, you have to print them out with, and consume a couple of trees, but you have to print them out and bring them with you. Okay. At the end of the exam only, what we will allow is for you to turn on your devices, scan the handwritten answers, and upload to Brightspace. That's basically the format of the exams. And as you can see from the class here, we are going to be trying to spread ourselves out a little bit to avoid or find another room, a bigger room. Anyway, we'll see. Let me go through the syllabus. Any questions up to this moment in time that I haven't covered? Okay, let me go through the syllabus. So we'll start with this kind of order. Initially, we will be very busy building a background on statistical learning theory. And there are plenty of theories that are going to fuse together into this class. Statistical learning theory is a theory that brings together information theory and optimization theory and others. We are going to occupy ourselves with primarily understanding loss functions. Why, first of all? The whole course is built around the question of why. Why, for example, we are to use cross entropy for classifying stuff. Why this, why that? Your best approach into this kind of course is to write down your own why questions and go to the office hours and have the TAs answer them. Okay, if again you cannot find the answers either using the TAs or ChatGPT or whatever, get hold of me so you know the answers. The reason why I'm suggesting this is that most likely our exam questions will be all around answers to the why questions. Okay, so if you want to be successful in the exam, make sure you understand your own notes very well and be able to have answers to all the possible why questions we can ask you. So after that, we will go through machines which are differentiable, like deep learning kind of networks, convolutional kind of networks, and finally we will conclude perception, which is we are going with the following kind of order. We are having sensory information, either initially it will be images or other kind of stuff. And the first thing that we are going to be processing is this sensory information is in the perception subsystem. And then the perception subsystem are going to contain a whole bunch of predictors. And these predictors are going to be predictions of classifications first, regressions, stuff like that. And then very soon they will become predictors that are doing object detections, stuff like that, right? Understanding the environment around us. Okay. And then, of course, we are going to also be concerned with more advanced stuff like we understand, specific seeing what objects are there, but most likely these objects are moving around or we are moving around. And therefore, we will be doing reasoning over time. To understand this reasoning process over time, as I'll explain in a moment, I'll show you a couple of videos. This is actually going to be needed to conclude the perception discussion. Now, immediately after perception, in the case where this kind of information at the input is coming in the form of language, we will be dealing with natural language. In this kind of space, we are ultimately trying to equip you with all the modeling kind of capabilities that you may have find useful, such as transformers and so on, to understand exactly what is really how language models can be built. After the course, if you understand these two, you will bring in these two to create multimodal reasoning capabilities. But that's after the course. I mean, this is an introductory course, and so we are staying at this moment of single model individually, right? Two individual kind of modes. Then we are going into planning. So we understand the environment. We can potentially understand instructions that are coming to us. And obviously, we are not really acting aimlessly in an environment. We have a plan to execute. So we need to understand planning. Classical planning is fairly thin in this kind of course. The planning, which is pretty, I will call it, involved in this course, is planning with interactions, which also known as reinforcement learning. Okay. Now, of course, we are in between planning. We are building some form of representation, which are coming from the space of logic. Now, the space of logic used to be what AI was in the 70s. Having said that, very recently, especially when you're trying to build verification of, let's say, statistical machine outputs, such as LLMs, you may actually use logic to drive the verification capability. So we find it extremely useful and current, despite the fact that it's several decades old as a topic. Therefore, this goes back to the book number 1, which I told you provides an encyclopedic sort of treatment of the topics on AI, and therefore you will find some good logical and classical planning treatment in several chapters there. Despite the fact, of course, we don't have the time to do everything from that book, which is 1,100 pages. So reinforcement learning is going to be the last thing we will do. We try via assignments to go beyond simple reinforcement learning and or even the project and teach you at least how to use reinforcement learning for something like fine-tuning large language models. Large in quotes, because obviously we cannot really tune large, truly large. We will tune probably pretty small models. Okay, and then just basically, that's basically it. Any questions on the syllabus? Okay, all right, that's, yes.
Are there any GPU requirements or any processor requirements in our computers to proceed with the course? As you mentioned, Google Colab will be sufficient.
Yeah, so the Colab is for those who does not have a desktop GPU computer at home or a laptop GPU computer. Does not. Everyone else has a GPU computer? Okay, good. All right, so the only advice I have is to use Colab. Now, there is an NYU resources that are equivalent to Colab. However, I found them in the past to be not very, again, it was several years old, so I do not know what's the current situation, but it's like more or less like Colab, but a little bit less robust. So Google has a following offer right now running, at least for all US-based students, to get a free subscription to Colab Pro with Gemini 3. Take advantage of that offer if you haven't already. I'm sure many of you have done it already, but in case you missed it, just take advantage of that. You need Colab Pro for your work here. If you don't have the Colab Pro subscription, the Colab will take your GPU at random times away. That's the only rental plan. There are obviously, for those who want to do something in AI space, I always advise students to purchase desktop computers and don't spend a lot of money on laptops, but spend money on a desktop, which is can run for 24/7 at home. And with Tailscale, you can connect a very inexpensive, thin and light laptop to your home computer and monitor the jobs which are running there. Well, that's probably down the road for those who haven't done it yet. Okay, that's basically it. So shall we get into the, oh, it's already 6. 5:45. Shall we get onto the technical side now? All right. I'll present the first thing. Okay. So also, I'm going to show you a video. Drink some water because I'm getting dehydrated. By the way, I told you I don't have any breaks in this class. Feel free to get up and use the restroom at any time. It's fine. And I'm going to stop to, as I said, 7:20. Okay. So first video. After we watch the video for a few minutes, I'm going to start drawing some stuff. So be ready to start writing if you are not. Okay. So in the first video, we have an agent guy over here acting in an environment. It's a game engine. Moving into sort of environment is way autonomously. Trying to keep up a constant velocity and having a plan to keep that constant velocity forever, because the environment is simulated, the road never ends. Obviously, there are some other agents around. Some of them are obstacles, but they are not going to impede our agent at the time. And if the agent finds itself in a situation where there is a slower car in front of it, in the same lane, it will gracefully change lanes, maintaining several constraints about acceleration, motors, and things like that, other constraints, and then gracefully move back into the middle lane. Okay, so I just wanted to take this as an example, and of course there's this strange green line sticking out of this kind of agent, which we need to understand what it is. So I am going to start drawing now. Okay, I got this thing first. No. Okay, so this is lecture 1. What is this today? 1:26, 27? No one knows. 23. Okay. 26. Okay. All right. It's really hot, so I'm going to sort of stay with the t-shirt and start drawing the agent. Okay, so I'm going to draw first a box here at the left, on the right side, called environment. And the environment block, this only scope of the environment block is to keep and maintain what I call the state, an environment state. What is an environment state? In broad terms, it's a state that includes a whole bunch of random variables. For example, if I tell you about the kinematic state of a vehicle, what would you include in that thing called state? That's a question for you. Kinematic state of a vehicle, what would you include? Huh? Acceleration. Anyone else? Speed, yes. Location. So it will be, you will put a dot and then you will put a vector that defines some kind of a velocity vector, right? Okay, and then but obviously, as a state here includes everyone in the world, right? So in this kind of hypothetical engine, right, that is running this thing. So it includes the state of other agents, the state of pedestrians, where they're located, blah, blah, and so on, traffic lights, whatever you can think of. So it's a gigantic state that no one is able to know for sure, but the environment is able to know it better. Now, on the other side here, this environment kind of sends some information to the agent, and the very first block that the agent needs to implement is called perception subsystem. This information is arriving, has some kind of notation. This sensory information, this agent, this car that we saw has, let's be very specific here. It could be many sensors, but I'm just going to stick to cameras, right? So the sensors, the camera sensors in the car, there are around 8 to 10 sensors, such as this in a vehicle such as this, and each one of sending, 30 to 60 frames per second, right? Images, right? Into the perception system. So it's a very high data rate, right? But for our purposes, we're going to abstract this sensory information with just, what is this notation? X underbar. What is X underbar?
Belongs.
Huh?
Belongs to.
Oh, the epsilon is belongs to R to the power of n, but X underbar, sometimes in books you see it in bold letters. Here we have I cannot draw bold, so I put the underbar to indicate that this is a symbol that is a vector. It's a vector. It's a multidimensional quantity. Okay. Now you're going to say, okay, hold on a second. I have, let's say, a vehicle over here, has a sensor, camera, just right in front of it. Imagine it's just one sensor right now. And looks at takes a picture like this. That's called a frame. How many dimensions we have in this image? 2. Well, most people will say 2. Having said that, remember that an image consists of what? Pixels. Each pixel has a value. And the pixel 1, let's say, can have a quite different value and varies independently from pixel 2, from pixel 3, and so on and so on. So, despite the fact I have 2 dimensions, I have H pixels in the height dimension, the height of the image, and W pixels in the width dimension, right? So how many total dimensions I have in this sensor? W times H. So if I denote by N, you should also know that my handwriting is prescription grade. So this means that this looks like an M, an N, or whatever. Just ask the question. Okay? Just write down the symbols. Sooner or later you get familiar with my way of writing. Just go ahead.
If it's a colored image, do we not have to worry about?
Yeah, right now we are taking the simplest case of grayscale images. In fact, we take other considerations as well. Like in computer vision, we have this kind of concept of dynamic range, right? Who has bought a TV recently? Who has bought a TV recently? No one is buying TVs these days. Yeah, okay, I understand. But if you go to the store, you will see this TV section with this kind of boxes called, have these big letters, HDR. What does HDR mean? High dynamic range. What is the meaning of a dynamic range in imaging? That how black can be, right? It's a kind of important consideration for the quality of the image, right? So your TVs that you have at home, especially the expensive ones, are you have, let's say, 16 bits of dynamic range in the pixel of each pixel. Here in computer vision, typically for us, we'll have just 8 bits. So the dynamic range means that of 8 bits means that the absolute black will be a 0, and the white will be 2 to the power of 8 minus 1. So from 0 to 255, all images will contain pixels, and each pixel will be an integer number from 0 to 255. Okay. And but that's outside of the concern of what we have here. Our main concern is that why we call this a vector. Well, we call it a vector because I can take an image and convert it into a vector. I can take the first row of the image, append to it the second row, append to it the third row, and so on. So I can create a very, very long vector. And this x now can be written, in other words, as x1, x2, ... xn. Do you agree? These are the contents of the image, a high-dimensional tensor. In other words, it's coming right now in my perception subsystem. And the job of the perception subsystem is to do many things, but we will take the simplest possible case called classification. They will classify, in other words, whether I see a pedestrian in front of me or not. That's called binary classification because the outcome is binary. In this domain, we call these outcomes with a y random variable. And when we do a prediction about that, we put a hat in front of, on top of it. And this is called a y hat. The y hat is a notation that says, you know, I will predict something. Okay, right now it's just predicting whether there's a pedestrian or not. And because the y is binary, it could be either a 0 or a 1. The y hat at this moment in time, at least, we'll never see that the y hat is going to be a number between 0 and 1, floating point number between 0 and 1. But right now, at least let's treat the y hat as an absolute 0 or a 1 prediction. In the video you watched, there are many more things happening inside the perception subsystem. The car is able to say, hey, is there another car coming on the other lane? Because I don't want to crash into it, right? So lots of other stuff is going on, like object detections and stuff like that are happening. But this one is plenty. Any questions on the first block? Input, images, output, and prediction. Now, you know, what is really the most determinant factor of performance in computer vision? Anyone has this information? The most, if you want to, if someone asks you what is really the biggest possible impact on the performance of any neural network or any other predictor you can think of, what would that be? Yes? Data. Data. Okay. Data is definitely the case because you have to train this thing. However, light is the most important thing. You know, take for example, a computer vision system has been sort of developed and using daylight images and put it to work on during the night, and you get a completely different performance. Right? So random light fluctuations, in fact, and probably for those who are driving, you probably recall sometimes you are driving in early morning, right, and then come up the slope, and then boom, the sun comes straight into your eyes, and then you need several hundreds of milliseconds for your lenses to adjust. During this kind of time, your vision is impaired until you put the visor down as quickly as possible, right? So similar things are happening here. And this thing is a statistical machine. What is the meaning of a statistical machine? A machine that sometimes spits out the right thing and sometimes spits out the wrong thing. It makes mistakes. Just like the ChatGPT that you are using at home, right? It hallucinates. Well, we don't need necessarily to call it hallucination here because these machines are much simpler, right? But they are making mistakes. So what is the form of the mistake? In one frame, there's a pedestrian in front of me. And in an exactly next frame, because this video feature coming like with 30 frames per second, 30, 60 frames per second. right? Very fast, right? Streams. The pedestrian disappeared. And then after a while, it reappeared again. Can the pedestrian disappear within 10 milliseconds? No. Even in animation movies can this happen. So you are certain that you need another block over here that we will call the probabilistic reasoning over time. Also known in layman terms as tracking, that even in the absence of perceptive information, even in the absence of white hats, therefore X's, it will spit out an improved version by hat that is definitely a subset of that state, and we call this S hat. Definitely, we cannot estimate ever this state. Can you even predict what happens when you're driving 20 cars in front of you? No, because you don't see anything. When someone slams the brakes 20 cars in front of you, you will get to observe that impact, right? Several seconds or tens of seconds later. So the only thing you have is a partially observed system. What happens around you, right? Two, let's say, 3 cars around you. And that's the best thing you can do. Come up with some kind of a good prediction about the state of these vehicles. Let's say, stay in the computer vision space. Of course, later on, I'll switch to another domain which has nothing to do with computer vision, and you will be persuaded that the same block diagram applies there equally. So your brain also is using this capability of predicting when you don't have information. For example, when I write with my prescription writing a word, you recognize the first, second, and third letter. You don't recognize the fourth letter, but you recognize the fifth and the sixth. So you are using the prior information that you have to cover the gaps that my handwriting left, and therefore correct for the imperfections of my handwriting. It's not only computer vision, but also natural language. When I go and hide myself right now behind an occlusion, behind this kind of desk, everyone knows exactly that I didn't disappear. I am behind the desk, despite the fact that you cannot see me. So this block is quite important for a variety of these kind of purposes. Obviously, the moment we have this kind of a state estimation, we know where we are, we know where the other cars are, what are the kinematics are. We can actually execute a plan. And this plan in that video was move constantly in the middle lane. And therefore, to execute this plan and satisfy the plan constraints, we need to have a planning algorithm here. You have to be able to define, in other words, a set of points that we will be moving in the subsequent few hundreds of milliseconds. And this was, by the way, that green line that was sticking out of that vehicle. This was a trajectory plan. Define a trajectory. That's why sometimes the line is a straight line. Sometimes it's an S line, because we change lane. And this line is fully specified by a set of points that we have to move at specific times in the future. And that trajectory is sent finally to a controller. This controller, you will not be dealing this course with controllers, know exactly all the mechanics of the agent, how a voltage or a current can create certain torques in the actuators of the vehicle, for example, and to execute and implement this plan. And therefore, the controller is products such as moving the actual car, right, to the specific locations that the plan kind of prescribed. And what will happen when the car moves? The global state is going to change. Global state changes. How the agent will get to observe that the state changed? By observing a new set of X's. And this whole thing will repeat and repeat and repeat. So this whole thing repeats constantly. As we will see, this loop will be later on mathematically described with a Bayesian rule. So some form of a Bayesian computer right there who is doing certain things. This loop will be executed, in other words, entirely on the probability space. Yes.
SL is basically an improved prediction using probability reasoning over time.
Yes. Improved prediction, however, this state is always a subset and imperfect version of this. We're never going to be able to predict the global state.
Professor,
Yes.
in the video, did you not need like a reward system to train the planner to what to do? Like,
So there is an arrow that I didn't draw yet. This arrow could or could not be present. In other words, this arrow may carry some information that is needed for us to be able to build planning algorithms, such as reinforcement learning. And this arrow is known as a reward signal. So planning can actually be done either with a reward signal or without. In fact, what you saw in the video is without. But many tasks are outside of this kind of domain, or even within this kind of domain. Reinforcement learning may be used in addition. Now, I told you that this thing is common as a block diagram organization across many domains. For example, in cybersecurity, what we have as X. One in the cybersecurity business here. Cybersecurity business. Okay, X is now a structured data. It's not unstructured, or could be also be unstructured to some degree. But in many instances are basically structured. You have columns, in other words. And for each column, you have millions and millions of rows. What kind of columns? The simplest possible cybersecurity kind of incident you kind of want to detect is a DDoS kind of attack. You have source IP address, destination IP addresses, ports, things like that. So you have sniffers who are monitoring traffic all the time, right? They're creating millions and millions of rows. And then the equivalent perception kind of subsystem predicts whether you have an attack or not. Obviously, you have someone who is going to correct again, because this machine again is statistical, predictions which are sort of, what is the name? Predictions which are bursty or something like that. So, then you have some kind of a better kind of prediction, and you may have a planner to start creating a plan that it will take actions into the network, like taking off servers of the network, switching off, closing out ports and things like that, right, to address this kind of incident. And obviously the environment here is itself very, very complicated. Good news is that the environment here in cybersecurity is the state over here could potentially, not entirely true again, but it could potentially for small deployments be fully observed. While in real life, in the physical world, it's never the case. Okay. All right, that 2 domains is plenty at this moment in time. And now we're going to go through, what is this? What's the video? Oh, another video, same kind of domain, where we have now a closed track, basic kind of track. Again, it is a greater kind of environment. You have the vehicle, whose job again is to not get out of the track. However, the architecture behind this is quite different than this guy, where the block diagram I just drew. So let me just draw the architecture of this, what is behind this kind of video. Here we almost crashed. So over here we have an environment. Again. With the state. X is coming in. But now we have another block. The agent is like a whole block. It's not decomposed, if you like, into individual kind of parts. And it's end-to-end differentiable. Now, it's a mouthful, end-to-end differentiable. What does it mean? It means that the whole abstraction from receiving the sensing information to spitting out actions is modeled by a very large neural network. And the reason why we are kind of interested in these type of agents, which this kind of architecture is kind of very popular nowadays, also known as imitation learning, is that in some domains, where the domain is actually very narrow, this architecture is very appropriate and has been battle tested. And the question to you is, why this thing cannot work in the video we had, first video? Why this architecture cannot work in the first video? And the reason why this architecture cannot work in the first video is that think about what data we need in order for us to predict all the stuff that needed so an action can be taken. I need to have access to an actual driver who is going to, in this small world, the racetrack, is going to start the engine, right? It's going to use the joystick to guide the vehicle around. And the joystick output is going to be the actions: acceleration, deceleration, and steering direction. Right? So the action here is very limited, first of all. These two things are different. This is action, this is acceleration. Goes to the negative deceleration and steering direction. Over here, the training data that I need are quite different. All I need is just images and their ground truths, images of pedestrians, images of apples and oranges, so I can have both y is equal to 1 and y is equal to 0. Train a machine, right, to predict pedestrians in front of me, let's say in the simplest kind of possible case, and that's basically it. I do not, in other words, need to have end-to-end kind of training data for that. What will happen if instead of this specific racetrack that I have trained that kind of agent, I change the track, and I have a track which is like in Manhattan. Well, guess what? The agent never saw this type of behaviors before, and the agent most likely will, in fact, it will be with 100% probability, crash into a building or some other thing. So it is quite important to understand the limitations of this type of architectures, because these architectures are very suitable for domains which are very narrow. For example, industrial automation. I have a robotic arm, and I can show the behavior, or I can drive the robotic arm to take an object from here and put it in a pallet. Take another object from here, put it in the same pallet next to it. So these actions are very, very deterministic almost, and very confined to a very specific narrow scope. So this thing is perfect for this. Anything beyond how to generalize these approaches are still in the research space, obviously. And this is where reinforcement learning can be used. But even Tesla vehicles today are still in this space. Even the FSD is still in this space. There are two different paradigms for this type of regions we will be concerned in this course. So now that we understand a little bit of what is really behind what we call an agent, now the fun starts, the videos are stopping, and math starting. So we will be now dissecting the first block, which is we call the perception. And we will start from a very, I will call it humble block diagram, yet another block diagram. This block diagram was invented by the godfather of statistical learning theory, Vapnik, when he was working in the lab several decades ago. And effectively, with this block diagram, he tried to answer the following question: what do we need to learn? What do we need to predict? What we need to build a predictor, which is going to behave well. Okay. So let's start drawing what we call the learning problem. Let me put in parentheses supervised. And Vapnik suggested that in order for us to build a statistical machine, we need to understand things that are quite outside of our control and things which is our responsibility. So the first part of the block diagram are things that are quite outside of control, and we need to understand why. So the first block that he drew is the called data generator. And we already have seen this notation. X belongs R to the power of n. A data generator for us will be mapped into nature. Nature generates images. Do we have control of what images nature generates? No. So a data generator generates some images, let's say. And another block next to it accepts this kind of things that are generated by the data generator. And this block is called a target function. That takes X as input and spits out a Y. In other words, the Y is a mapping via this target function from X. And of course, everyone here wrote the equation in kindergarten, Y is equal to f of X, right? So nothing extraordinary here. We just wrote the same thing with a kind of a block diagram. Now, I'll tell you what's going to happen in maybe this lecture, next lecture, I do not know. But this block diagram and these letters will end up being components of probability distributions. Okay? But right now, think about it as kind of a deterministic kind of point of view. So the target function is something that we have absolutely no control and no knowledge about. And it's actually a very complicated function. Imagine a function that takes an x that has the 128,000 dimensions and spits out a 0 or a 1. That's basically what we drew for there. It's very complicated. We have no clue about it. The only thing, however, we have someone over here that is called a sampler. This sampler, out of the infinite mappings between x and y, samples certain pairs of x and y mappings that we will be calling examples, and spits out what we call a data set. We're going to put the eyes here. Spits out m examples out of these kind of mappings. The sampler is also something that we have actually no control of, and we will play certain tricks. For example, the sampler will, for a task that involves face recognition, will tell us, I'm going to draw a line here. This is the border between what we have no control, which is above the line, and what we have control, which is basically our statistical machine, which is going to be drawn below this. Because I want you to build a statistical machine to do face recognition, and I'm going to give you 1 million faces of white people, 10,000 faces of black people. Okay, I build a statistical machine for face recognition. What will you think will be the performance of this statistical machine for black people? Not very good. This happens in real life, by the way. Other tricks that we'll play. Start deleting some dimensions out of X. In other words, the first problem was the so-called class imbalance problem. Second problem, deleting columns out of X, which is called the missing data problem. So all sort of tricks the sampler will play, but we have no option. This is basically the data someone gave us, and we have to do whatever we can with the data. So the D here is a calligraphic, stands for data set for now. So Vapnik said, okay, fine. What I'm going to do, since if I had known the F function, the predictor will be extremely trivial. But since I don't, I will build some form of evaluation system of glorified trial and error sort of predictor, where the first block down here, I'm going to call it hypothesis set. And we'll spit out a function g. Since I want to find out something about G, I will build a hypothesis. What means building a hypothesis? I will assume something about G, about F. I don't know anything about F. I'm going to assume something about F, and I'll call my assumption, hypothesis, G. I want to know about something about the function F, therefore I'm going to use another function F, another function G. If somehow, magically, G is very close to F, I'm in a good shape. Now, obviously, this function G, since it's going to be used for making predictions, I hope everyone understands that the function G, that's the aim here, to find a function that it will accept my X, an X potential that I have never seen before. Never seen this specific pedestrian before. It's not part in any way out of this data set D. However, I know that one way at least to adjust hypothesis, functions in this case, is with a parametric way. Who can give me the simplest possible functions you learned in elementary school? Yeah, y is equal to mx plus b, straight line. What are the parameters of that straight line equation? M and B. Let me call these parameters W0 and W1. By having the knobs W0 and W1 and changing them, I can have the line go like this, straight to the parallel axis, to the x-axis, whatever I want. Okay. In other words, I have examples I can use to sort of visualize parametric lines. But this can also be extended to any line, even not straight lines, quadratic lines, things like that. I can plot a quadratic line like this, and I can plot a quadratic line like this. I can plot a concave and a convex line. Okay, fine. I can do whatever I want with G, still though the problem remains. I have no clue about F. So he said, fine, I need to have someone over here that I will need to define that he called objective or loss function. We will be using both terms in this course. A block, in other words, that will receive this G and will spit out a scalar as a signal to me being now an optimization algorithm. So G will be going to this function. This function will do something. Spit out back a scalar. I will call this scalar capital L, and I will denote it that it is indeed a scalar. It belongs to the set of real numbers, and in fact, it's positive. And this scalar L will indicate to this big block called an optimization algorithm, whose job is to, all the job there is to it, is to change the W. What is changing the W will do, just like in a straight line, it will change the function. And if we design, again, anything below the red line is our responsibility. We have to design that objective function as well. If we design the objective function in the right way, our L, if it is small, if we inject the following behavior, if L is small, that's going to be a signal that we are doing okay. if L is large, it's a signal that we are not doing very well. And therefore, the optimization algorithm will try to make more adjustments to it. And finally, this optimization algorithm is going to work again in a kind of an iterative way. And after doing a lot of iterations, we're sick and tired of it, and we call it a day. And we will call this W that the optimization algorithm found to, I will call it W star. Star is a usual notation in optimization to indicate the best W we ever found. And this W star will then be used in the so-called final hypothesis. To give us a W hat that is, as you can tell, this. We are entitled now to a prediction. We labored to find a W star. We cannot obviously change X. X is given. It's an image. Take X, tell me if there's a pedestrian or an apple, or whatever, not pedestrian. Binary classification. And using now the W star, the only thing we can do is plug it into G, plug in the X, get away. That's how we spit out a prediction. Obviously, these are all fairly abstract, but we will go through an example in a moment. But yes, go ahead.
Does the loss function not take the data set as a input?
We'll see what was going to happen. The loss function itself is going to obviously need to be taking two things into consideration. How a prediction Y, that at any instance in time, in this kind of long iteration, has been at some point in time, at any instance in time, I can use this guy, no matter what the W is, to have prediction. This function will have two arguments, the Y hat and the Y. So I need to design it in a way that if my predictions are for similar X's, are very close to the ground truth that I know that it is, then my L will be smaller. And if not, there will be a larger. Obviously, the whole discussion here is very deterministic, but will be probabilistic finally. Let's understand what happens in a deterministic way and connect what this algorithm is actually doing, which is spitting out the W star, to when the right time comes to that this algorithm will have to produce something that has to do with some statistic of probability. Some statistic, like a mean, a conditional mean, in fact, the probability. But let's not run before we walk. That's a general kind of block diagram for supervised learning. Let's apply it to a very simple problem. So this simple problem is a regression problem. We move away from binary classification. Just look at the regression problem. And we will be dealing with a very straightforward regression problem that is on your side. This regression problem is called linear regression. And this data set that we will be using here to apply the mapping diagram is synthetic. What is synthetic means? Means that we generated it out of nowhere, out of some, we already knew the target function. We picked up a target function and we generated some kind of mappings between X and Y. Okay, so don't be confused with the vertical axis here. This is a Y and this is an X. So the simplest possible problem, prediction problem that we have, we ever going to come across in this kind of course is this one. We don't have even multiple dimensions. We only have n is equal to 1. And let's assume that X is square footage, and let's assume that this vertical axis is price. Okay, and we're in a real estate business. Okay, so we have mappings between square footage of houses and their price. Yeah, don't look too much why the fact this goes like this doesn't really matter. What is the input to the statistical machine? The blue dots. This line over here is plotted to confuse everyone. No one knows about this line. This line was the target function I told you. No one knows anything about it. Okay? It was primarily used to generate the blue dots. Okay. So let's follow what the Vapnik will do. So for the problem of linear regression, I have this data set, X and Y, and I have my blue dots. Okay, these are the blue dots. In other words, someone gave me a table of X and Y, X1, Y1, X2, Y2, dot, 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 XM, YM. M is 10. If you count the dots in the website, it's 10. And what is the prediction problem? Well, the prediction problem is a price prediction problem. If I give you an X you've never seen before, in other words, an X in between the two dots over here, give you this kind of X. Give me a price, because I want to deploy this model in an investment house, a fintech company, who is going to buy houses coming into the market. Okay? Obviously, you do not want to overpay, but also you do not want to underpay because others will win the bidding process. So that is the problem. Come up with a model that it will do good price prediction. If everyone is following what we try to do here, what the Vapnik said is to come up with a hypothesis. And everyone here is entitled to a hypothesis. Again, we are trying to assume something about the underlying target function f, which we know nothing about. And therefore, I am offering my hypothesis about the prediction. Yes?
That's a function g, right? That we're
Yes, I'm just plotted my own version of the function g. Is this a valid hypothesis? It is a valid hypothesis, and make sure that you understand that you should not be making the following mistake. You should not be using your brain to tell us that this is a bad hypothesis. The machine is completely stupid, so it will need to go into designing a loss function to evaluate this hypothesis. Can the machine plot? No, the machine cannot plot. The machine is not going to use matplotlib because very soon this n from 1 is becoming like a billion. So I'm going to write down the hypothesis. Let me get my notes here because make sure that I have this thing in order. So I am going to call this G0. In fact, I'm going to color it as orange. Where is W0 in the figure? In the plot, where is W0? It's right here. How many hypotheses can I have with, in other words, I only have one parameter. Right now, I have one parameter. How many hypotheses can I form with one parameter? Infinite, because I have one knob. If I start changing the W0, that line goes up and down in infinite possible positions. Okay, so I kind of cheated a little bit, and I didn't draw the line over there on the ceiling, right? I put it around the data somewhere, right? And I will claim that this is the best possible G0 I can have. Okay. Another guy here has another hypothesis. This is the green hypothesis, and this green hypothesis is G1 of x comma W is equal to W0 plus W1 x. Now W is a vector, two parameters, W0 and W1. Again, I could draw any green line, but I drew probably one of the best green lines for this specific data set that optimization algorithm will probably find. Can I move on into plotting G2? How? I only have one feature x. Who said x squared? X squared. Someone says, you know what, you may have one x, but I can start forming any features I want. In other words, what is a feature? A feature is a representation of my data, and I can take x and multiply it by itself. Okay, you can take x and multiply it by itself 2 times, from x cubed and x4, all the way to whatever number. I will tell you what is the ultimate number we'll reach here. But someone could say, hey, you know what? I will go to x is equal to 2. And therefore, the moment I have an x squared there, I have a quadratic line. So don't be surprised by this kind of shape. It's the first nonlinear line that I can have, right? Nonlinear function that I just plotted by effectively using my capability to define using monomial terms and additive constructs. Someone in middle school told you about Taylor series expansion. Right? Do you remember Taylor series expansion? Okay, some of you at least. Where someone told you, you know what, I can decompose a function as an addition of many, many terms. So I can form, in fact, any function I want from adding more and more and more complicated powers to the power of 3, 4, 5, 6, all the way to 9. And in fact, I'm not going to bother you too much with this kind of construction. I'm just going to go straight into 9. And if I plot this line, I'm taking this function over there that goes through all the data points that someone gave me. I said, okay, fine. I mean, you are a good artist of plotting lines. Having said that, where is my model? I'm waiting for the model to be deployed so I can make some money. And I said, we have now a whole bunch of hypotheses. let's evaluate each one of them. Yes, go ahead.
This should happen at G11, right?
Okay, I know what you're getting at. Let's not stay on the starting from 0, starting from 1. Okay, let's stick with that on that. But there are two ways to do the same thing. So I need a block, which I call in the mapping diagram the objective loss function, to evaluate this thing. I will send as input the hypothesis, right? And I'll get back what? A positive scalar number. So I have to sit down and design this block, this function. Now, in what is to follow, I will follow the so-called hand-wavy way of designing that function. And recall the moment later on in maybe in the next kind of lecture, or maybe in the next lecture, we will come back to this moment and tell you, you remember we designed this loss function in a hand-wavy way. Now you know where this function came from because it will be derived out of some information on theoretical principles. So this loss function, or I will call it loss function because it will indicate to me whether or not I'm doing well or not with respect to a prediction. Is going to be designated with calligraphic L, and definitely will have two arguments, y and y hat. And definitely the intuition behind it is the following. At the end of the day, I have a whole bunch of hypotheses. Look at the red hypothesis over there. How I use the hypothesis to make a prediction? How? For an X that I have never seen before. Anyone? How I'm going to use the hypothesis? I'm going to take an X that someone never gave me my data set. Go there. That's my y hat with respect to G2. For that specific X, that's my y hat for that house. That's how the money I'm going to pay for that house. And okay, so the y hat is what I will get out of that hypothesis. Now, how can I potentially use the data that someone already gave me? I'm doing the following kind of trick. Instead of looking at X's that I've never seen before, I will look at the X's that someone gave me, and I'll go and see if the y hat for the G2 is close to the y that someone gave me. And in fact, yes, if this is the X, this guy over here, and for that specific X, I go and see the function G2, what it gives me. It gives me a very similar price, right, to the one which is in the table. So what I'm going to do, since I want to, the output of this loss function, if you go back to your notes in the block diagram, will be a scalar, right? I will have, definitely I will see in that kind of loss function the difference of yi hat minus yi. Do you agree? That's the intuition. How much different is the predicted price versus the reality? Now, sometimes, depending on the data point, this difference will be either positive or negative. As I told you, either I overestimate or underestimate is one and the same wrong thing to do, right? So I don't care about overestimation and underestimation. All I care is the absolute difference. I can put an absolute function there, or I can simply square these errors between the prediction and the ground truth over here. Is similar, not entirely similar, but for this discussion it would be similar. And right now, at least I have some numbers. How many numbers I have? M numbers. I have, for each data point over here, for each X, I have a number. What am I going to do with looking at m numbers? Not really much, because I'm after a scalar. I'm going to sum these numbers up and divide by m. This function definitely will result to me into such a single real number, which is positive, and therefore satisfy the needs of the requirement of the Bartley diagram. And this function has a famous name called
Mean square.
we call mean square error. It's an error because it's an error between prediction and ground truth. Squared because I'm squaring, and the mean comes from the fact that I'm taking the sample mean of the squared errors. So this is called mean square error. And again, remember the moment that mean square error will came out of this kind of intuition and hand-wavy way of describing the problem. But as I said, later we will derive. Yes.
The m equals 9 and m equals 2 that you wrote.
This one indicates some kind of number that captures the complexity. Is everyone okay? What's going on?
Oh, chair went through the floor.
You okay? No, you're not. So we call 911. Are you sure? Can you enter this call? There's another call over there. Okay, you hit your head though. All right, sit here. And then in 5 minutes, I'll ask you about your name. Sure. All right. Okay. Yeah, I'm going to report this anyway. Not for you specifically, but for the hole that we have in the room. So the chair fell into that hole. Yes. Okay, I found a sandwich and some people left in a hurry just before the class. I'm going to report that as well. Okay, so what I was saying something about the mean square error. I'm done with the mean square error. Okay, so now I have the loss function. I can evaluate this hypothesis. And if I go around, by the way, I was telling you something about capital M, right? Capital M is just like a proxy to complexity of my hypothesis. It's definitely capturing how many weights I have, or anyway, except for the bias term here, which I call bias specifically, but how many of the fractions of features I have in the hypothesis. So an m is equal to 9 is a much larger complexity, more complicated hypothesis than an m is equal to 2, for example. Which is a notation that I want to make sure that I use a little bit later to tell you something. So I can now evaluate the hypothesis. Out of all the hypotheses that I just drew, which one completely minimized the mean square error?
Last one.
The 9. In fact, it made it 0. So very happy about this outcome. I go to my boss, the CIO, the Chief Investment Officer of that real estate company, and said we found it. We found a very good model about cost pricing. They happily deployed it. And at exactly 3 o'clock a.m., I received a phone call. And they announced to me that the company went under and I'm fired. So then kind of puzzled by this kind of outcome, you know, in corporations like this kind of real estate companies, someone has to be blamed. This way about it. In fact, there are 3 pillars in corporate America. The first pillar, if you don't know it, is land grabbing, you know, the classic behavior. Oh, you know, I will do it. I will develop the best model. Then the second behavior is under delivery. You know, kind of overestimated my abilities. And the third one is passing the buck, finger pointing. Someone has to be blamed for my under delivery. So without any doubt, someone has to be blamed. Who is to be blamed though, except from me? But I lost my job anyway. So who else is to be blamed about this? Look at the Vapnik diagram. Someone has to be blamed, and this someone is
Loss function.
the loss function. So the loss function has to be blamed. In my attempt to minimize this thing, I came up with G9 as the best. If this thing was something different, G9 would not have been the best. So this condition that we kind of led us to this kind of fairly complicated kind of hypothesis is called overfitting. Overfitting is a well-known term in the kind of layman terms, in the sense that what it means is we have over-invested in terms of number of parameters and associated features, because as you can see here, we have, is this a linear or a non-linear model? Most people will say non-linear, okay? But in fact, it is a pretty linear model. What makes it linear? The answer is in the way that in your site captures this hypothesis we just drew. What is this thing called in math?
Feature transformation.
Feature transformation is a phi, but this thing, this operation, dot product. Dot product. Is a dot product a linear operation or non-linear operation? Linear. Tell me about the dot product a little bit, just to remember what you done in grade 1. Okay, so you had X transpose W, let's say, right? Both of them are vectors. So what is this? Let's assume that we are talking about just a straight line, okay? So what is X? X is 1X, because you only given a feature, like square footage. And W is, you told me, W0, W1. In order to form a dot product, you have to have vectors of exactly the same length, right? So what is a dot product? You told me it is going to be, so not X transpose W, the other way. Do it the other way, because that's the way I'm using it. W transpose X. So this one will be W0, W1 transpose 1X, right? Don't confuse this X as a vector and this X. This is the scalar feature that someone gave you, right? And this is the vector, and I put this number 1 there because very conveniently, if you do this dot product, you'll get what? W0 plus W1X. Wasn't this the G1? It was the G1, right? Similar way, I can build the G2, the G3, and so on and so on. So the reason actually I'm calling it a linear operation, as you can see, is I am linearly combining features phi, I call them. Features phi, I call them. We will see now also in neural networks how these features phi get to be formed. But we have a fraction of feature 1, add to it another fraction of feature 2, add to it another fraction of feature 3, and so on and so on and so on. So it's a linear combination of features. Plus the W0, which we call in layman terms a bias term. It doesn't matter if you want to call it bias term or something else, doesn't really matter. The feature present here is x to the power of 0. 1. This one fully justifies the term linear model. We just built a linear model that, and we should never confuse the fact that we are using linear operations here to form nonlinear hypotheses. the nonlinearity of the function we plot comes because we raise x to the power of 2, 3, and so on and so on. We never raise w to any power. So this is our sort of end result. Now that we have plenty of time since we're fired, we have to go back to that loss and function and see, since it is to blame, what can we do better? So this overfitting, first of all, is best if we detect it before we deploy. So at the very least, we will not go, claiming that we found a model. And obviously, that kind of model, G9, can also be visually understood why it is a very bad model, because for an X we have never seen before, the investment house invested this money, right? And that's how they went back. We will be calling this approaches of detection. The detection part is trivial of dealing with overfitting. The compensation, in other words, the addressing overfitting in a way that someone can semi-automatically pick up the right model complexity M, capital M, is something which is a bit more. So the addressing the detection of overfitting is going to be trivially done as follows. Since someone gave me this table over here, take this table. Instead of using all M examples, I will use a subset of them, let's say 80% to build a model, but I'll keep the remaining one, the 20%, locked into a drawer. And then I'm going to, when I have my model and I want to see how it is doing, I'm going to use this other data that I have locked and to see, okay, is my y hats close to the y's of this other locked data. So this data that I lock, I will call test data set, and the other, I will call it the training data set. Okay? So test and training data sets are two different data sets, orthogonal. And in fact, in the trade, we have also 3 types of data sets that you will come across. I'll write them down. So the detection of overfitting. I'm going to take this M and I'm going to split it up into 2 parts. The M train and the M test. Not equally, I told you 80-20 or something like that. And therefore, I will have now 2 losses that I'm spitting out. 2 scalar numbers. One is called L train, and the other is called L test. So if I do this, at the very least, I have found a way to detect overfitting as follows. I can take every hypothesis from M is equal to 0 to M is equal to 9. And as I told you before, I will spit out 2 losses. It's the same model during training, right? After training, we'll produce the L train, this guy. And when I'm taking out the data that the model never seen before, we'll produce the L test. So I can see here the following kind of behavior. I can see this kind of shape. But one thing is notable. When I do have overfitting, the difference between L train and L test jumps up considerably. Because visually, I just explained it to you moments ago. When I went to the G9 and took an X I never seen before, these differences are really huge. It's a really complicated function. If I have another one, like G8, G7, and so on, I see some kind of flattening. So G8 to G3, very similar performance, and the difference between L train and L test is still small. And over here we see very small differences also between L train and L test. However, the absolute values of those are much larger than here. So in terms of detection of the overfitting, the capability is there. In terms of avoiding another condition called underfitting, obviously we have to be mindful of. But for an iteration model and a model that iterates across multiple kind of hypotheses, the best model that someone will find, right, will end up being, if you follow this approach, from m is equal to 0 and iterate all the way across to l is equal to 9, the best model will be, someone will find, will be G8. In fact, maybe it won't be G8. Maybe, let's assume it is G8. But is this the best model you want to deploy? No, why?
It's a simpler model that forms almost the same.
So the intuition is, why we deploy an 8 billion parameter model if you can get away with 3 billion parameters? Again, don't think about the toy example we have here. Think about the inference costs, which are the largest possible costs in this domain, right? Obviously, you can get exactly the same performance, in fact, for 1/3, more or less, of the differential costs. So this concept is called simple but not simpler, or Occam's ratio. But that's besides the point. It doesn't really matter what it's called. One I think, however, is kind of certain. Can we have an approach where I don't have to do this? I don't have to go from m is equal to 0 all the way to m is equal to 9, but someone guides me to automatically tune to the right model complexity. And that someone is called a regularizer. So these approaches, called regularization approaches, are many, but today we will be dealing with, in fact, for the next 10 minutes, I'll try to wrap it up. We will be dealing primarily with one that has to do with changing the loss function. So I'm going to describe the intuition about one regularization approach, which is basically under the headline of addressing overfitting. So I'm going to change the person to blame, the L, which I'll call now L reg, into be the LMSC, which was the one that drove me to getting fired, plus L penal. And I want to introduce the following behavior. The following behavior is as follows. When I do have overfitting, I want the loss to be lower or higher than LMSC?
Higher.
Higher. What is the intuition behind it? You know, the optimization algorithm is doing some form of informative search, okay, to spill the beans. Let's assume that I'm in a three-dimensional parameter space. G is equal to 2, W0, W1, and W2, right? So we are, the optimal W, the W star, is a point in this room, right? Because we are in a three-dimensional parameter search procedure, right? I'm trying to find where is the W star. And I'm looking in a space where this space, this specific kind of W, will, together with a combination with the loss, right, is going to create a hypothesis that is going to overfit. What is the behavior I want? I want the optimization algorithm to move away from the overfitting region. How the algorithm will move away from the overfitting region? it will see a large L coming in back into it. That's the only signal. What it is, but most likely it is a fan or a bomb. Anyway, so the algorithm will say, I do not want to be going close to this sort of region. I'll go find some other region. So by having an L penalty that when overfit is very large, and when it doesn't, it's very small, this is the right behavior. That is my new loss hash. Sounds like my refrigerator. Okay. So from that kind of perspective, I will present to you what we will go through in detail, it seems, in the next kind of lecture. And we will design, we'll need to find the intuition behind this choice of L penalty. Now, mathematically, what this is, first of all, lambda is a scalar. Forget about lambda for the moment. What is this operation? Anyone has seen that? Yeah. This is, underneath this is a summation, but that's called a norm operator of a vector. Right? Again, go back to the review sections in linear algebra, the norm of a vector, what is a matrix by vector multiplication, this type of stuff, dot products, stuff like that. So a norm of the vector W is W0 squared plus W1 squared plus W2 squared plus W capital M squared, square root of that. Is this a scalar? Yes, it is. So in terms of dimensionality, we are in good shape. This is a scalar, therefore this is a scalar, this is a scalar. So we have a norm square, we just remove the square root. We have a scalar still. So what we will do is to see how this term made some kind of sense. And the way to see it is we'll go into this kind of piece of code, right? And we go and set M, the one that was resulted in overfit. M is equal to 9, and run. And see what W comes out of it. And the W comes out of it is shown in this picture. These are the index of the W vector. And these are the values of the W vector. This axis. And you can see that we have 400,000, minus 400,000. In its attempt for the red line, the line that or the blue line here in this presentation, to go through all the data points, the W vector itself exhibits huge swings. When we go back to the source code and change with something you have to do at home, change the M is equal to 9, M is equal to 3, let's say. This thing doesn't work. So we have found a signal, which is, I'll call it an organic signal. Organic in a sense that it's coming from within the problem itself. It is the W that I had to estimate anyway. It's not, I'm not using some external kind of thing that I can use. So when I have overfitting, the norm squared of this W with a 400,000 as an element and minus 400,000 as an element will be a huge number. And when the M is equal to 3, it will be a much, much smaller number. It's the M is equal to 3, I didn't overfit anything. So this is the intuition behind the choice of the W, norm of W. Could be a normal W, could be the norm squared of W. Both of them are possible. So, if I am to do that, I will come up with the following result. the W, let me call the W star reg will be W0, W1, W2, W3, close to zero, dot, 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 close to zero. What the optimization algorithm came up with that new loss, he said, you know, stop this switch off the higher order terms of the polynomial. What is then the effective order of the polynomial? Instead of being 9, we still expand the 9 coefficients for the model, right? But the optimization algorithm said, you know, the only appreciable W that I have for you is from W0, W3. Yes, you still need to use the 0.01, 0.0005 and things like that terms over there because that's the hypothesis you gave me, but that's your problem. So I stuck to the M is equal to 9, the capital M is equal to 9 kind of model, at the expense of expending significant inference cost of 9 billion parameters, let's say, right? I have found a way that depending on the data, right? And depending on that I'm facing, right? I will have a model that will be semi-automatically adjusted for me. That is basically the whole concept of regionalization. Now, someone will say, yes, but you are stuck with M is equal to 9. Well, this is why NVIDIA is there for us to help us out. Because if I throw to NVIDIA tool this parameter vector, NVIDIA will say, are you stupid? You can just remove this, do model compression, and I'm just going to keep this for you. And I'm going to be deployed in my CPU with 1/10 the cost you would have spent otherwise. Okay. So you can use TensorRT or some other tool, right, from AMD and others, to eliminate weights which are very close to zero. And then life is good. So to conclude, we saw the method that is doing the semi-automatic way now, but this whole story, unfortunately, is not complete because we still have that lambda. We still have someone who adjusts that L penalty relative to the mean square error. So next time we'll conclude this discussion by understanding what this lambda is doing, which we'll be calling a hyperparameter. Because we want to separate this type of parameters, which we'll consider this some kind of form of an outer loop parameters, to the actual model parameters, we'll call the inner loop parameters. So there are some things for you to do during the weekend, right? Make sure that you are all in Discord. Make sure that you watch out for the assignment 1 and do the development setup. It's not urgent again, but you need to submit something for assignment 1. We will allow you to do that with Colab as well. I'll talk to you next week. Yes.
Do you have time for a quick doubt?
If I have time, while I'm packing, yes.
Yeah. So I was noting that in the loss section, we had put in a weight penalty for a weight. So our model prioritizes low values of weight. Is that right?
No. What this L penalty has, the reason why the W there is the behavior that we have observed by plotting and therefore estimating a norm, the norm squared, such that the norm squared becomes a huge number when you have overfitting and not a huge number, much less when you don't.
Okay. That's okay.
Yes.
Typically, you wouldn't want to penalize for W naught, right? Otherwise, it's always W naught would always be penalized and sent to 0.
Okay, so there is the bias. Okay, so the bias is because the bias itself is part of the model. It's already accounted for by the optimization algorithm. Right. It will tune it
Right.
to whatever value it is.
Right. So for ridge, we can keep it outside of the isoline or the norm, right?
Or you can just keep it inside. It's better to keep it inside than outside.
Yeah,
Because you have to optimize it once.
Oh.
But I think
Yeah, that's correct.
Okay. It's okay. The only concern is that what type of project you will face, right? And to what extent Colab will grow. So what kind of notebook you have?
I have a Lenovo.
Lenovo? Okay.
It's a yoga, it's not a.
He's over there.
Okay. I think it should be okay. It should be okay.
No. What's your favorite name?
Thank you.
I'm gonna ask him.
I get your copy.